Okay, is there anybody in here who wasn't in here for the first half? Okay. You guys may be a little bit confused, because I don't think we can start over. All right, so where we left off, we'd finished talking about sort of the read end of things in sort of this execution processing into this little runtime system. So let's see. Now we sort of got the async write portion of it, which would kind of be done when we're executing one of these little active messages. So let's take a look at what that interface would look like. So we're back to our kind of connection class. And we had, for the async reads, we had sort of those three functions. And here's for the async writes. So first of all, we've got the interface. So that's the async write, which we're going to give it the action. We're going to give it some handler. And then this is sort of this worker thing. And this is the one that's actually going to be scheduled in the little local queue. So that async write doesn't actually do anything. It just sort of enqueues the worker to be done in that little local queue, so that we can go on and do some other work while we're waiting for that asynchronous write to happen. And so then we've got this write handler, and the sort of, we don't have that sort of two-part process like we did with the read, where we had to read the size and then read the buffer. Although apparently I've been told now that that may not be the best way to do it, that there's a new feature in Asio that can potentially allow you to do the read in one pass. But so let's take a look at that async write. So again, as I said, it's just launching off this sort of asynchronous operation. So we got that little local queue. We're going to push this thing in there. Only thing we have to do is we have to keep this action alive. So we're going to stick it into a polymorphic pointer. That's why we had the little clone method in that action type from before. For the people who are new in here, I promise I'll get to stuff that's a little bit less, you have to jump right into it. But we're almost done with sort of this section. So we're going to put it in here. Again, we're doing the shared from this, and we got this action pointer. It's another shared pointer. Here's the async write worker. So we're going to create this shared pointer for the output buffer. We need a shared pointer for the out size. Now that seems a little silly because it's small, but again, we got to keep this thing alive. We don't actually have it in the data structure here. We're just sort of passing this along. And the reason for that is that we had that in size and that in buffer in the connection class because we were only doing one read at a time. So we weren't queuing them. Here, we're possibly having multiple writes going out at a time. So we have to sort of keep multiple output buffers alive at the same time. Thus, we need the shared pointers here. And so then we're going to use this std vector of const buffers. One of the things we mentioned back in the first part of the talk was doing these scatter writes. So where I've got multiple buffers and I want to write them. Well, the way that you do a scatter write with Asio is instead of passing in one buffer, which is what we've been doing for all the other examples, we're going to pass in an std vector of buffers, specifically these two. So the first one is this shared pointer, and this syntax here is a little bit fun. So we are dereferencing the shared pointer. We're getting the raw pointer from it to create the buffer. And we're doing the same thing with the size of it, and the same thing here. And then we're going to pass in those buffers that contain the raw unreferenced counted pointers to Asio. And then we've got this connection handler. And we're using boost bind. We're binding in the connection as a shared pointer to keep it alive. That's where we've got the references to the shared pointers for the buffers to keep them alive. And then there's the user-supplied handler, which is this std function up here. So we're doing a lot of little tricks here to make sure that everything stays alive after we exit the scope of this function, because, of course, this is an asynchronous operation. And so here's the serialized partial function. So we looked at this, the deserialized before the break. And again, we're using this Boost.Io streams container device. So this is a little trick to give us an IO stream that reads from a std vector of characters. And here we've got our action pointer. We create our Boost serialization archive. And we do the serialization, and we've written it. And then we go ahead and we return the raw message pointer from here. All right, so here's the connect. This is another point that was brought up at the break, that I should have been doing my connects asynchronously. And it's absolutely right, I should have been. In my sort of use cases, I'm mostly thinking about, hey, all the clients are going to connect up front, and it doesn't really matter if the connects are slow. But I'm just going to lie and say that this is because I wanted to show everybody how to do a synchronous connect, because maybe you want to do some synchronous stuff. But this is probably slow and probably shouldn't be done this way. For me, it doesn't really matter because it's a one-off cost. So here we've got our resolver. Now, I usually am not going to do this with, I'm just going to pass in IP addresses, so I don't really have to worry about any DNS resolution, but maybe you want to. So this is the sort of the class that's going to deal with this. You can pass in just sort of localhost or an IP address, and it'll deal with that as well. And then we've got this resolver iterator. And basically, what that does is it goes through all the resolutions that the resolver picks up. Hopefully, you just have sort of one thing that resolves that address. And so then what we do, we go and check, hey, are we already connected to this guy, whoever's calling us? Because if we are, if they've connected to us in the past, we're going to try to keep the connection alive so we don't have to go through this process again. And then here, we're got a little trick here. So presumably, the clients are connecting at startup here, and we kind of want to tell them to wait while we're bringing things up. So we don't do this deterministically. We just kind of say 6.4 seconds should do it. I don't remember how I picked this number, but it worked for this example for me. So 6.4 seconds was more than enough time for me to pick here. So we're just going to go and we're going to try to connect to the server. And then we're going to start the async reads. So now we sort of looked at this little runtime. And now let's kind of write a little hello world example with this. So we're going to have two or more nodes. One of these is going to act as the bootstrap node. So everybody else connects to it initially. And then the server is going to send an action to all of them that is going to print out hello world. And after that, we're going to shut down. So running the example would look like this. Now in the code on GitHub, I've got some command line processing stuck in there. So you can do the -- port and whatnot. And we go ahead and run it like this. And I was just running it on my laptop. I just do remote host equals localhost. So we need some tool here to invoke something on all of the different nodes. So the runtime on the bootstrap node is going to have a handle for this. We're going to pass it a main function and a node count in its constructor. And it'll invoke the main function when the number of connected nodes is the same as the specified node count. So in the actual runtime that I work on, the two hardest parts are starting things up and shutting things down. We have a 5-phase bootstrap protocol to bring our runtime online, where we go through all these different sort of bootstrapping the system on top of itself to bring up various different services. And we need those services to be able to communicate with everybody so that we can bring up even more services. So you start off with something like, hey, we send one sort of fixed message to the server, and then it sends us back some addresses saying this is who you are, this is your handler, here's a list of everybody else that we're going to talk to, and sort of do that process to bring the system like this up. So here's sort of the runtime's initializer. And that's sort of this F here is sort of our main function for our little system. And the wait for is how many guys are we going to wait to connect to us. So here's our hello world action, which uses our action base class. So it's pretty boring. It just prints out hello world, and it stops the node. And serialization is pretty boring because this is just an action. It doesn't have any data associated with it. The data associated with it is the type. So we're serializing this action, and then on the other end, we're going to deserialize it as hello world action, and that's the information. The information is that the thing we're deserializing is hello world action. And again, we've got this magic here and this magic here to make the serialization of the base class pointer work. And here's a sort of hello world main. So we're going to start off, we got this. I thought I got through these slides without using auto or any C++11 features, but I guess I didn't. But so we got this auto connections. We're going to get a list of everything that we're connected to. And here's our count. And then for everybody that we're connected to, we're going to go ahead and send out an async write with this hello world action. And then when this is done, we're going to count down. And when we reach the last guy, when the last message has been sent out and completed, then we're going to shut everything down. So now we're sending it out, taking in that list of connections and the count there. Now, again, in this example, we're just got 2 threads, so I don't have to worry about the count being decremented by more than one guy, because all these handlers are that's going to be invoked in only one of those threads, the IO thread, as the event's complete. So what would happen if hello world main waited for the async writes to finish? Anybody? If we moved that call to RT_stop from the lambda into the hello world main, and we used a condition variable, said, no deadlock, why? Well, because we need to use the execution thread to serialize the action before they can be sent. And if we suspend the execution thread at the OS level, waiting for the async write completion handlers, we'll have a deadlock. So this is one of the fun things about these sort of runtime systems is if you've got a bunch of these execution threads that their job is to sort of execute the user code, and if they do any IO stuff, and if all of them are doing IO stuff at the same time, like, say, waiting on a mutex, and the thing that comes in that would unlock that mutex happens, you've got a problem, because there's no execution resources to process the thing that will unlock the mutex. I remember in the early days of our project when we would run into this frequently. The thing would deadlock on 15 nodes, but on 16 nodes it would be fine, because 15 of them would deadlock, and the 16th guy would spin and do the thing that would unlock everybody. So it's kind of an all or nothing approach when you get into these asynchronous systems. That you need all of your things that can block at the OS thread level need to be done in a certain pool where you're doing no execution of sort of user code. And the user code can't do any blocking. It can't call any boost mutexes. It needs to use your special constructs. Even something like with certain allocators, you could run into problems. Or if you're calling anything into the operating system that could potentially lock things up, could be a problem. So let's talk a little bit about futures. So the one thing that this sort of system's missing is SGD future. We have this way of that async write thing that we could use to start a write where we would pass in a completion handler. Well, that's not particularly nice. It would be nice if we could, instead of having to pass in an explicit completion handler and say, hey, this is the thing we want to do, it would be nice if we could get back a future as a handle to this. And so that's sort of what the thing that I work on, this HPX system, does. So it gives you these futures that represent these remote computations that represent, communication, I/O, futures to represent any form of sort of asynchronous events. So such a feature would work with 2 parcels here if we want to have these to represent remote futures. One's going to start executing the remote action, one to send the result back to the caller. So we kind of got something like this in the remote case for using a sort of distributed future. So I got Guy over here. I need to do something over there. So I go ahead and I send a message. Message gets over here. Start doing this thing. This thing finishes. While I'm not waiting here, I'm not blocking up this resource, it's doing other stuff. And then once we're done here, we send the result back, and then we resume the consumer thread. And we've sort of got a system for suspending and resuming our user tasks so that we don't block our scheduling resources. So what else would we need? Well, we need user level threading, because we need to be able to suspend tasks not at the OS level. So we want to be able to suspend our little tasks. So boost context, boost coroutines, both of those are all right, but they're not fast enough. They don't work with large enough quantities. So we sort of have an in-house thing that we use. And we need some sort of global address space that can sort of manage the lifetime of these features and manage the lifetime of these objects. So that's that sort of back parcel that returns the result. So that's this thing. We call that a back parcel. That needs to keep the thing alive. It needs to keep the future object on the first node alive. Or the thread itself needs to keep them alive. As it turns out, both of them need to sort of keep the thing alive. When you suspend a thread, the synchronization primitive that caused it to suspend needs to stay alive. Otherwise, you're going to have a hard time waking it back up. And if we just pass along local memory addresses, that's problematic. So we need to have a notion of a global reference count or global memory management. So implementing a global reference counting system, global sort of shared pointer. Does that sound like fun? Does anybody here? Anybody have a scheme for how to do it? As it turns out, it's really tricky to do that quickly. So what we sort of do is we have this notion of a globally unique identifier. We sort of bake the reference counting into it. So there's other sort of reasons why you want to have user level threading. It's useful just in terms of breaking up a problem locally, right? That's why we have std future and std async. So that's a little bit older. We aim for smaller target thread lifetimes these days. Our goal is to sort of have the ability to have millions of tasks per node per second with very, very small lifetimes. We want to have very, very fine-grained parallelism. So we want, that one maybe, yeah, that's still correct. So that's sort of our goal, is to have the amortized overhead for creating a task in user space be less than a nanosecond. Or less than a, is that right? Less than a microsecond is what that should say. Because less than a nanosecond would be a little ridiculous. So we talked about global address space. So those sort of actions are kind of cool, but what's more useful is this notion of components. So maybe we want to just have our regular classes and then have them have methods that we can send over the wire. So that little action class we were playing around with, that's cool, but it would be nice to just be able to write your functions and then have some way to just turn them into sort of remotely callable things. And then to be able to do the same thing for methods. And so then we have to be able to address those. Promotable. I'm going to skip through the HPX slides, I think. I'm going to go to the sort of bonus section of the talk, which has a bunch of little tips and tricks. So I've got a couple slides in each one of these. And each one of these are fun things fun problems or solutions to problems that we've run into playing around with Asio and serialization and object transmission. So if anybody here wants to shout out if they're interested in hearing about one of these, we can kind of go through in order. We could just kind of pick some of these. Anybody? All right, we'll just sort of jump through these in order. So I mentioned this a little bit before, but it's not so good if I've got an array and I copy it when I'm sending it over the network, because I shouldn't need to do that. I should be able to just, if I've got an array is just basically a contiguous block of memory. I should be able to use that as my buffer and pass that through to the operating system, and it should be able to use that to actually do the write, and I shouldn't need to copy it anywhere there. Now, the scatter-gather sort of can be problematic there, because when you have an array, okay, that's one thing. But what if you've got, some data structures, you got like 2 arrays, a couple arrays, you want to try to reduce the number of copies here, but you've got non-contiguous blocks of memory. So my solution to this was to have this special zero-copy archive. It uses an std vector of Asio buffers instead of streams. And every contiguous block of memory is basically placed into a buffer. And we do a 2-pass write and read. So the write, pass 1, we iterate over all the buffers, and we create an array containing the sizes of each buffer, sort of metadata array. And then we write the size of this array, and then we write this metadata array. Pass 2, we iterate over all the buffers, and we write them. And we're going to sort of write them as just 0 copy. And on the read, we go and we read the size of the metadata arrays. Then we read the metadata array. And we iterate over all the sizes. We set up the sizes of all the buffers. And then we do the read. And then we iterate over, and there's the read. So this is sort of what it... I don't know if I have an example of that one. I do not. All right, so next thing is sort of the TCP congestion. So a lot of people don't know about this. In Asio, you can pass in all your regular socket options, all those flags and whatnot, using these Asio options. So for like TCP, you can do Asio TCP, : no delay. And this is an Asio option class. Then you can go do socket.setOption. So this one's particularly useful for us in HPC because we do all sorts of abusive things. This is one of those abusive things that we do. So it reduces the TCP/IP congestion by buffering small outgoing messages. Buffering's nice, except if you really want low latencies. If I want my messages to fire as quickly as possible, I don't have bandwidth problems, I have latency problems. So that's why you would turn this off. So that's something like what the Nagel algorithm looks like. This is really bad for me because I just want to get the messages fired off as quickly as possible. So QuickAC, this is another one. So we got to do this to disable the buffering of acknowledgments. Again, this is something where I'm just trying to reduce latencies, where I don't want to do any of this buffering. I'm not concerned about bandwidth. I'm not concerned about efficiency. I don't care if I'm sending a lot of small messages because I've got plenty of room on the wires. But I do care how quickly these things are getting around there. So one of the fun caveats here is you have to set this after every read operation because on Linux at least, it'll reset the flag after every read. So we end up, we get something like this where we have to do this every read operation within our little code. So this is sort of scary to me. Anything that can potentially delay me finishing dealing with a message for up to 500 microseconds. That's a long time for me. So when latency is more important than bandwidth, it's a really good time to use it. So real-time systems, when you have a high-throughput network that you can just abuse, you don't have a lot of bandwidth limitations, when you don't care about congestion. So bad things can happen if they're buffered and Nagel is on. A sends data to B, B receives data from A, buffers the ACK. A tries to send a small message to B, and the message gets buffered because A hasn't received an ACK for the first write. So you sort of have these two, if both of these are on, you can have some nasty interactions, which will delay your small messages from getting sent out. TCP is not really designed to send these very, 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 very small messages. And remember, because of that, the way that those ACK delays are allowed to be delayed up to 500 microseconds. So this can sort of stall out your event processing for quite a bit of time. So I/O service pools. So we talked about I/O service, and we sort of used it in a single I/O service thread context. So this is not something that I think is actually in Asio. I think this is something that my boss hand-baked and is sitting around in our it's either an Asio example or it's something that is in that repository that I have linked. But basically, it's a pool of I/O service objects and STD thread objects, with the idea that maybe you want to have, you've got a 16-core system, you want to have 15 cores that are processing your execution threads, but then you want to have 4 threads that are sort of I/O threads, or maybe you have some different mix of things, depending on how your hyperthreading is, how many cores you got. So you got one STD thread associated with each one of these I/O service objects, and each of them is calling I/O service thread run. And so I/O service thread will normally return if there's no work available, but we use a little trick to keep these guys processing in the loop. So they are just waiting for I/O work to do. They're just spinning there, basically. So we just sort of do a round-robin scheme. So when you want to go and send some I/O work, you sort of send it out to one of these guys, and then the next time you send it out to the next guy, and then to the next guy. And this can be used to parallelize the invocation of completion handlers. Yeah. Sorry, can you come up to the microphone?
Why are you using multiple I/O services when 50 threads or 100 threads can easily run on the same service, and they'll pick up the work as it comes? It's just perfectly normal. And actually on Windows, that's going to give you the best performance because it uses a completion port, and it has a very interesting and optimized algorithm for choosing which thread to wake up and to avoid cache misses and stuff like that.
I'm not sure why we're doing it that way. My guess would be, we're not just looking at Windows, so my guess would be that
it's the same on Linux as well. It's just I'm not sure the Linux has this hot thread option, but it works exactly the same way as the Windows one. You just fire 50 threads, and all of them do run on the I/O service, and they'll dequeue operations that are scheduled on that in the thread in the way that they are coming in. So I don't see much option or much problem.
We may be doing that for reasons of NUMA issues, to keep data local to threads. I guess my question would be, what would be, if we're round-robining the I/O work, what would be the disadvantage of having multiple I/O service objects? That they run out of work? Okay, that would be a fair point. Yeah. But it does trade off sort of locality for, plus you got to synchronize them too. If you've got multiple threads accessing the I/O service object,
there is a synchronization inside the I/O thread, inside the I/O service. So unless you have something, but there is actually, there's something called a strand that actually can give you simulation of asynchronous. So I was just wondering why you're doing this rather than the other one.
I'd have to look at the code. Let's talk about that one a little bit afterwards. You may well be right. All right, so let's see which one do I have next. That's service pool. Still on that one. A little example there. So bitwise serialization. So this is another little trick. So if you got a type that's just plain old data, writing a serialization, one of those serialized methods might not be the fastest way to serialize it. You can just specify by specializing this is bitwise serializable type trait, and just tell serialization, hey, you can just treat this as a sequence of bytes. So of course you should only do this for very certain types, but it can be nice and fast. So there's this macro for conveniently defining it this way. Yeah. Yeah, yes, but yeah, that's a fair point. There's some cases when this is nice to do, some cases where you'll shoot yourself in the foot. But if you know that this is safe to do, if you know that if you're not worried about network byte order, if you're just doing it, say, for making backups. So we use serialization as well for checkpointing our stuff, where we're just writing it out to a file. And for something like std array, it's nice to just do it this way. It's an std array of a POD type. So we do this also for, this is some code that does it for types that have elements. So for like a tuple, std tuple, so that if we have an std tuple, just, if we have an std tuple of types that are bitwise serializable, make that std tuple bitwise serializable itself. I'm pretty sure this one's kind of generally safe-ish. We haven't run into problems with it. All right, so there's this array optimization that you can do with Boost serialization. Let me see where the array example code comes up. It's not going to be on the slide. So basically, if you've got something that's like an std vector, of int. Serialization would normally, if it was an STD vector of, say, pointers to base classes, you'd want to iterate through it. If it's an STD vector of int, you probably don't want to iterate through it. So there's this trick that you can do for this. So first of all, you got to enable the array optimizations for your archive. And once that's enabled, there's not an example of that. So I don't have the syntax up here, but this little trick's useful for, we use this when we're sending STD vector of double, which is one of our major use cases, being that we're doing scientific codes. And so it's nice because it just puts it all out in linear time. All right, so exporting templates. This is one of the complaints people sometimes have about serialization is you have to do some crazy stuff if you got a template-derived class and we want to serialize it through a base class pointer. So we have a trick for this. We register each of these instantiations explicitly. Normally, you do this at compile time, but we've got this trick that uses this customization point that got added to Boost serialization, and basically we abuse runtime type information and to get a sort of unique identifying string, and we do this at runtime. So we don't have to deal with doing a explicit one of these for every different instantiation of the template type. So this is sort of what the syntax looks like. And this is something we've been trying to get upstreamed into Boost serialization, because right now, as it is, you have to instantiate for each one of these ATs, you'd have to instantiate this. Serialization, and we hash the runtime type information because we don't want to just have the string in there. Okay, so portable archives. So we have these two portable binary archives, which are compatible across systems with different endianness, and these are basically taken from the serialization examples, and we've kind of modified them a little bit in our code. So these archives, they use the Boost endian library under the hood. We're using a container type with value type of char instead of a stream for the input and output. And the other thing we do is we don't always want to write that serialization : archive, which you saw in the text archive. It'll actually write that in the binary archive, which has always annoyed me a little bit because I'd rather just have, don't write a signature there if it's something that's sort of, you're sending a lot of small messages. Now, obviously, if you're just dumping in some huge archive, it's not a big deal. But if your message is just one int and then you've got that string in there, that's not particularly fun. Took us a while to figure out that one. We had to actually do a TCP dump and look at the packets, and we were like, what's this string doing in here? All right, so that's pretty much it. Again, there's the link to sort of the slides. Any other questions? If not, we'll go ahead and end a little bit early. I think we're not too far. All right.